So the title of the talk is Milnor-Thurston Determinant. And the Ruelle transfer operator. And in some sense, it's sort of it's a kind of ending parenthesis on a long piece of historical work, starting with Milnor-Thurston and passing by a lot of intermediate persons, in particular, for instance, Ruelle and Balladine Ruelle and other people. And the setup is, in some sense, one of the most trivial dynamical systems you can imagine. So I'll put some small symbols like this, saying that this is the first part, and then there'll be a second, and then I'll come back a little bit to some of this. So the setup is what you call 1D, piecewise monotonic map. Should put continuous perhaps also into the continuous monotonic map or monotone map. And then when you have a piecewise continuous monotone map, so what can you then do about it? Well, you can study how the dynamics act upon your space. And let me give you just a drawing of some examples. So you have an interval AB, and then you have some cutting points or critical points. You have a dynamic, which is a map of defined partially, because I will actually not define at the endpoints, and in particular, so the map might not be continuous, like for instance this. So you have some critical points inside, and then you have, we will also be interested in denoting these something. So we would have like, here we have like two internal critical points. And out of this we have like three intervals, so t plus 1 intervals. And on each of these intervals, so let me call them something like I0, I1, I2. On each of these intervals you have a map, F, IK. IK is an open interval, and then you have a map which is strictly monotone and continuous. So the map is partially defined because it's not defined at these critical points. I don't define it at A and B either. But apart from that, you can start looking at what is the dynamics going to do with the interval. So we have first Z1, we have just the three intervals, the collection of three open intervals, which form a partition for the domain of the function. Say initial partition. And then you start looking at, if you iterate the map, then you have to refine your partitions in order to be able to define it. So you look at the refined partitions. So it will be, you might write like Z1, and then you look at all intersections with pre-images of Z1, F minus N plus 1, Z1. So these will be, this will correspond to a refined partition. And then what you, one of the, say, topological properties that you can associate with this dynamics is what happens with the number of partition elements as n goes to infinity. And it's not difficult to see that, for instance, it's very difficult, no, it's very easy to see that if you take the number in the m plus n's refinement, then it's not bigger than the number Zm times the number in Zn. So it means that if you take log, it's subadditive. So the topological entropy, which we may define as limit 1 over n log number Zn, exists. So this is one of the first things that dynamicists would consider studying in this context. Now, the computing effort in calculating Zm is quite heavy. So the computing effort for calculating Zn, well, if you need to calculate Zn, what you do is that you need to keep track of all inverse images, backward iterates of the critical points. So you see that when you look at the f squared, for instance, when it's defined, then you need to look at what happens when do you land on the critical point. So this needs to take care of all backward images of critical points. And they tend to grow in number like Zn. So actually the computing effort is of the order of exponential of the number, which is n like exponential of n h top. So this is just in a naive picture that we'd like you would, if you want to calculate it, you would do like this. And it works fine in some cases, and in other cases it works a little bit less. When you have a so-called finite Markov partition, then it's much easier in some sense, but I'll not talk about this. In the general case here, and that's sort of the part 2, it is that Milnor-Thurston came up with some method for computing this topological entropy. And what they did was they constructed a determinant. So I'll talk a little bit more about how you construct it actually a little bit later on. But for the moment being, let me just say it's a formal power series. In some variable, in a variable called t, say. And the formal power series dmt of t, mt for Milnor-Thurston, is expressed in terms of powers of t, of course, but then of forward orbits of critical points. So this uses forward orbits of critical points. Now you would say that to me that actually the forward orbit of critical points is not defined because f was not defined at C1, but you have limits to the left and to the right. And what they do is that you look at what the left limit point and right limit point are doing during the dynamics. And in particularly, you will only have up to order n. So if I look at computing effort here is much less than in the first case, because it uses just the forward orbit. So if you want to get to order t to the n, say in this determinant, the computing effort would be of the order simply of n. So instead of having a computing effort growing exponential here, you just have a linear growth, and they would actually precise the same precision in the determination of the topological entropy. So now they have this determinant, but so what can they say about it? So their theorem, say it started in, so it's Milnor-Thurston, and the first part of it actually started already in 1977, but the proofs was published much later, actually, only in like 1988. And one of the reasons was that they had difficulties with a certain part of it, and then others was that perhaps they were a little bit lazy in publishing. But there are two parts of their theorem. So if I say that I take T star to be exponential of minus topological entropy. So I didn't state this, but obviously this here is never negative, but it could be 0. So this here actually is just smaller or equal to 1. And the first observation for the DMT is that DMT is not just a formal power series, but it actually becomes an analytic function in the unit disk. So it is analytic in the unit disk. So we have write D like this. And so in the interior, it's an analytic function. So zeros, for instance, are particularly will be isolated points. And the first part of their theorem is that if T star is smaller than 1, so this quantity here, then it is actually a 0 of their determinant. And the second part is that if you take any number smaller than that, so if T is smaller than the T star, then the determinant is not 0. Now, the first part was is proved by relating in a very ingenious way. So just say proved by relating forward and backward orbits. I should say in a very clever way because it's non-trivial, but you can do it, say, if I talk about it, it would be like half an hour to sketch it, but I won't do that. And I believe it was actually mostly Thurston who came up with this in the beginning. But then he didn't manage to see in the beginning why it was, say, the smallest 0 of the determinant. And then that, I think, was where Milnor came in. And they then added a proof, which was using what is called a zeta function, so it's Artin-Mazur zeta function. Which essentially keeps track of periodic orbits. Now you need to worry a little bit when you want to keep track of periodic orbits because if the map is not expanding, then you might have a lot of them and more than you want. But you have to manipulate this in a slightly different way. But then they derive some magic identity. Which is that if you take the Artin-Mazur zeta function here, and then you multiply by their determinant, then it turns out that this has no zeros, no poles. Zeros, no poles in the unit disk. So the structure of the, say, of the zeros of the determinant. So let's see, we have the unit disk like this. And then we have T star somewhere here, which is the smallest 0. And then in the circle here of that radius, you have no zeros in here. No other zeros. And but you might have some zeros outside, which could actually like what Vivian would call resonances in her talk. So you might have some other zeros. And on the border of the circle, the function need not be defined. So it might have an... sorry, there might be others. There could actually be others here. Yes. But then none inside. And this T star might actually even be a zero of order bigger than 1. So it's not like in Vivian's talk that was like simple eigenvalue or something like that. But the fact that you have no other zeros here means that numerically, if you compute it, then you're sure you got the right value. Now, I would call this a very indirect proof, and I think Milnor-Thurston agrees with this. So, very indirect proof. And particularly, the proof actually uses the fact that for a particular map, you can verify it's true, and then you make continuous deformations of the map, and you verify that when you make the deformation, it remains true. So they obtain a little bit more than what I was saying here, but with a very indirect proof. So, so you might say that's it. So you have a nice theorem here, but there's still something nagging here, which is that how come that you get around this backward forward orbits, and what are the relationship between the two? And then there's actually a third thing, which is that you might describe the topological entropy in this setup by a Ruelle transfer operator. So there's the Ruelle transfer operator. There are much more general transfer operators than this, but in this particular context, it would simply be that you take L phi of y, and you say that it's the sum of phi of x over all x which are primitives of y. You should act on some function space in order to start talking about this. So let's act in the beginning on, say, B, AB, which would simply be bounded functions with a uniform norm. And when you do this, then you realize that Ln1, so if you take the identity function constant together 1 equals 1, and you look at the value of y, it simply counts the number of primitives of nth primitives.
But since there are points where things are not defined, you have to exclude.
I mean, I should say x in the domain of f such that this is true. So I don't write it, but here x in the domain of f, because as you correctly say, I mean, it's not defined everywhere.
But you do take functions, I mean, in the set-theoretic sense or up to measure 0?
No, this is really just bounded functions. So there's no measure theory here. So this counts the number of nth primitives of y. And so we're looking again at backward images. And it's not so surprising to see that if you look at the spectral radius of this operator acting on bounded functions, it will simply grow in the same way as, this will grow in the same way as the topological entropy, like the Zn. So this will simply be e to the h top. Now, the spectrum in itself on bounded functions is completely without interest otherwise, because the spectrum here would just be e to the h top, which is sitting here, but all this disk here will actually belong to the essential spectrum, so you won't really see anything else. So this is for the spectrum of this operator acting on bounded functions with a uniform norm. Now, if you stay with the bounded functions, then you don't see much. So what you tend to do is that you restrict to a smaller subspace, and then you see some structure emerge, some spectral properties emerge from this. And in particular, what we do is that what tends to do in this context here is to look at boundary variation functions. So we restricting.
In a trivial case of the identity map, for example, then nothing happens, so it's the identity function.
Yes. And then the topological entropy is 0.
Yeah, but the identity operator is just spectrum, which is
1. You're right. You're right. Thank you. So, in general, actually, yeah, it's true. It's contained in the disk here, and in many cases, you will get the full disk.
You would need some mixing or something, right, to pull this?
Yeah, probably, yeah. So, at least in this space here, it's very difficult to get some interesting spectral structure out of it. So, let me say what happens when you restrict to the space of boundary variation functions. Now, in that case, it turns out that the essential spectral radius will shrink, at least if the topological entropy is positive. So let me... Okay. So the essential spectral radius of L, but acting now on boundary variation functions, in my context, will just be 1. So in any case. And if the topological entropy is positive, strictly positive, then you have the following picture here. We have a disk of radius 1, which in general will be the essential spectrum of the operator. Then we have exponential of h top here. And that will be a largest eigenvalue. As in the other case, there might actually be on the same radius. You might actually have other eigenvalues here. You might also have some eigenvalues sitting inside. And when you look at this picture here, then you see that there's actually some quite big resemblance with this here, except that you have just inverted T and the eigenvalue. So in this context here, Baladi and Keller, in a paper in 1990, constructed actually for this space of boundary variation function. They constructed a zeta function. So I call it a Ruelle zeta function. For the operator L of this type. Actually, they do it in a more general context with weight, something like that, but it also works in this case. When the map is expanding, for expanding maps, then in fact the Ruelle zeta function here and the Artin-Mazur zeta function will be pretty close to being the same. So usually you can choose them to be the same, but otherwise there might be some correcting factor. But this here has no poles, no zeros in the unit disk. And furthermore, for the Ruelle operator, for this one here, and for this zeta function here, there's an intimate relationship between the zeros of the zeta function, or the inverse zeta function, and the poles and the eigenvalues of L. So L lambda is an eigenvalue. I should say actually for lambda bigger than 1. So again, outside the essential spectral radius. Lambda is going to be an eigenvalue of our operator acting on PV, if and only if 1 over lambda is a zero of the zeta function here, which is the same as zeta function here, and therefore it is going to be a zero of the Milnor-Thurston determinant. So somehow the also multiplicities coincide with orders of the zero. So that's really a perfect relationship between the zeros of that Milnor-Thurston determinant and then the spectrum of this operator here. Now, so this obviously indicates that there's some relationship hidden here between what is this operator doing and then what is this Milnor-Thurston determinant doing. The operator, recall, is using, in principle, backward iterates of the map, and Milnor-Thurston are using forward iterates of the map. So it's a bit strange, actually. So looking for dualities. So I think Davide, a couple of years after the first appearance of these zeta functions, started thinking about this operator L, which are using backward iterates, should somehow be looked as, one should look at the dual operator, some dual operator of this operator, which should correspond to looking at forward images. So he did this in, I think it's like 93, and then published a little bit later on, 96. And what, at least which is my interpretation, which might be not completely up to standard, but he looks at some operators, some or even integral of operators, which acts on BV functions. And then there's a kind of dual operator let me write L tilde, which in fact takes bounded functions in the uniform norm and maps it into the cell itself. Now, this space is unfortunately not quite the Banach dual. Of PV. So a priori, I mean, the spectrum of this and then of this is a kind of dual operator. You can't really say, you have to be very, very careful of saying something about the identity between these spectral values. But he arrived at something which is very ingenious, which is to introduce a trace. So, what do you call this? Sharp trace. Written like this. You could actually tell that eigenvalues of this operator and eigenvalues of this operator, which are outside a certain essential spectral radius, would be coinciding. Showing that, say, let's call it peripheral eigenvalues of L and L tilde coincides. Again, this is a little bit indirect approach, but still, I mean, you can actually obtain some information. If you know something about the essential spectral radius for this, for instance, you can deduce something about this without doing the first calculations. Then Baladi and Ruelle. So I think that was probably 95 or published 96 also. The years might be a little bit. Then studied directly the Milnor-Thurston determinant, but with weights, and showed that the zeta function of Ruelle and say I'll call it a Milnor-Thurston-like determinant. Had the same peripheral structures, meaning that in particular they have the same zeros. So again, it was there's a few things here, which is that it was through the sharp trace. So they used this construction here, and also they needed some assumption on the weight that it should be continuous. Now that could probably be improved. And it was already improved actually by Sebastian Goodsell in 2001. He managed to say that the weights needed only to be continuous at periodic points. So that's sort of a first thing, but still was sort of still the proofs are somewhat indirect, and they did not quite apply directly to the Milnor-Thurston determinant at first. So then what I started doing it was 2 years ago. I was sort of studying. I was supposed to give some lectures about Milnor-Thurston determinant. So I was studying it quite hardly, and then studied together with my wife Tanlay, and we produced a paper on this sort of the standard approach, you can say. But it was still nagging in my head for a long time. If there's not a way to see directly that the Milnor-Thurston determinant and the Ruelle operator had a direct relationship. So then what I found finally was that yes, indeed, there is a relationship. So that was something I discovered last year. So there's a subspace let's call it x0 of boundary variation functions, which is invariant under the operator L. And then having a dual, so and this time it's a real Banach dual, so x0 prime, which then would contain this dual here, but be somewhat bigger. In particular, actually, it would be allowing for representation in terms of real nice L infinity functions. So allowing for representation so I'll call it as say B0, which corresponds to like L infinity functions, but on a slightly different space. I'll return to this in a moment.
So here the functions are strict functions or up to measure 0?
No measure. That's also why I write small L infinity, but on an uncountable space. So what happens is then that sigma, so the spectrum of L acting on x0, is the same as the spectrum of the dual operator acting on x0 prime. And because of this isomorphism, I'll talk a little bit about how it works. That's the same as the spectrum of the operator, induced operator on this space here. Now, the upshot is that this operator here has a very explicit representation. So there's a calculation which shows that L, now the last one here, may be written as an operator S minus PS. So there are two operators, bounded linear operators, acting on this last space, such that S has norm 1, and P is a finite rank, and the rank actually is related to the dynamical system, which is D plus 1. So why does this help you? Well, it does because if you remember actually,
For the unweighted
so this is for the unweighted transfer operator. Yeah. So this is related to the fact that the weights are equal to 1.
well, also the rank thing, right?
Well, it could be smaller. Excuse me. Yeah, no, you're right. Yeah, no. Then it's much. Yeah. So it should be. I mean, it works for constant weights, but yeah. So what we are aiming for is actually to describe not the essential spectral here, which we can't really do anything about, but what's going on outside. And then if you take some value lambda bigger than 1, then you notice that if lambda minus L is invertible, now because of this construction here where you have real isomorphism between the dual and the isomorphism between the representation, that's really the same now as just L minus L hat being invertible. But L minus L hat being invertible, so what does it look like? It's lambda minus S plus PS invertible. And when is it invertible? Well, lambda is not an eigenvalue of S, because lambda is bigger than 1 and S has spectral radius 1. So I can put it outside the parentheses and say 1 plus PS lambda minus S inverse. But this here should be invertible. And finally, this was invertible, so I can remove it. So it's the same as this here being invertible. But P is a finite rank. So here we have a genuine finite determinant, or finite rank map. And if 1 plus this finite rank operator is invertible, that's if and only if the determinant on the image of P of 1 plus PS lambda minus S is different from 0. So if we call this something here, d lambda, then this, as I said, is a finite rank. So this really involves just a computing of a d plus 1 matrix. And how does it look like actually? It looks like determinant image P, and then of you might write it like 1 plus P and sum of S to the K, lambda to the K. So I may, if I have the explicit representation, I can compute this. And then the revelation, say. It took me like 3 days of computations where I did some sign error or something like that. But then finally it shows out that d of lambda here is in fact Milnor-Thurston of 1 over lambda. So this gives the precise information that I was looking for, namely that zeros of the Milnor-Thurston determinant are the same as the zeros of this here determinant, which are then the same as lambda being an eigenvalue. And then there's a little more complication showing that the order of the zeros will be the same as the multiplicity of the eigenvalue. So we get a perfect correspondence between the Ruelle operator spectrum and the zeros of the Milnor-Thurston determinant. So this, of course, doesn't tell you much about how did I then do the computation and how do I get this space B0 out of my setting. And the idea is really to choose the right subspace. There are two things which actually help in this aspect. So first of all, I was talking about the map was not defined on critical points, but it's defined when you take limits from the right-hand or left-hand side. So the idea is you should actually make systematic use of limits, right and left limits. Systematic use of, well, you can call them, actually, point germs is one word. You may also call them directed points. And if you geometry, you might also say that we're looking at the unit tangent bundle. There are different ways of looking at this. So the idea is that if you have a point on the real line, then you would like to associate to this two directions, x plus, x minus. So x, call it x hat, sort of a directed point, would be something with an x and then epsilon, or you might put them together like this. And then the epsilon would indicate whether you're coming from the right or from the left. You also naturally introduce an order, which is that if x is smaller than y, then you would say that they are ordered like this. So I intertwine actually the two, defining an order between the two. If you have a map defined partially, say, so this is like just one branch of these things up there. Then in this example here, for instance, the right endpoint will actually be mapped to f of v plus, and the left hand would be f of u minus. And then we would call this, say, the extended map. So I would write, if I call this u hat, then I would call this here f hat u hat. So you see that every time you have a little branch like this, you can actually extend it to looking at map of point germs. And then you get a nice map defined on sort of all the point germs between the two. In particular, if I look at my original map here, something like this. Then from A to B, you actually have 3 intervals, which now become point germ intervals. So you have I0 hat, I1 hat, I2 hat. You have the point germs from B plus to B minus, which are simply becoming now partitioned into I0 hat, ID hat.
Without exceptions, without...
Exact. So now this is actually becoming a perfect partition. And the reason for doing this is precisely that the extended map here is actually defined everywhere now. We also have these signs, so I didn't actually talk too much about this, but the signs mapping A plus to B minus. So that would be mapping to plus or minus 1, which are sign of monotonicity of the branches. So here do plus 1, minus 1, minus 1. And then we have the product along orbits, which are the product of these signs along these extended orbits. Now finally, and this is maybe done again. Some. Finally, the Milnor-Thurston determinant is actually called a needing determinant, and the reason is that they look at relative positions of orbits of the critical points to the critical points themselves. And there's something called needing coordinates related to this. So if you take C somewhere among the critical points, C1 up to CD, then you would like to say that a point germ is either to the right or to the left of the critical point. And the way you write this is to write plus 1/2 if x is bigger than, hat is bigger than c, minus 1/2 x hat less than c. Now, one of the important things about this notation is that you never get 0. Now, when t is an auxiliary variable, then you construct for any initial point, you construct the needing coordinate, which gives you rise to a needing invariant of Milnor-Thurston. Now, it's not quite that formulation, but it's equivalent, which is that you look at a generating function. You look along forward orbits, as I mentioned. You take this sign of monotonicity along the orbit, and then you multiply the relative position of the last point relative to the critical point in question here. So this is their construction. And then they write a matrix, Mij of t, which is going to be the following. So I'll write it down. So I Cj plus t minus theta Ci Cj minus t. Now we do that for j equal to 1. So for the internal critical points, I define this. And I define for Ci a plus t plus theta Ci b minus t for j equal to 0. So these look like some magical things just popping out of nowhere, and at present that's the case. But so this is so that there are a certain number of critical points. So this is d plus 1 times d plus 1 matrix. And then it happens so that the Milnor-Thurston determinant of T is the determinant of this matrix. Now, if you look at this as a formal power series, then the coefficients here will always be plus or minus 1. Here we'll get plus or minus 1/2. If you look at this here, coefficient will be plus or minus 1 or 0. So coefficients all like plus minus 1 or 0. So these define nice analytic functions in the unit disk. And this here becomes then an analytic function in the unit disk. Now, this is the Milnor-Thurston determinant, but in the version which I developed recently with Tanley. So then you could go on to prove why Milnor-Thurston actually works, but that's not what I want to do. I want to say, what is the relation with this weird subspace I was talking about?
So here it's analytic, complex analytic, or what do you when you say function, you are?
Coefficients are all real. So it's analytic in either sense, but it's here it's just analytic in the variable t, complex smaller than 1. I mean, these all have values plus minus 1/2. So every coefficient in these power series will stay bounded, and so you get an analytic function in the unit disk. I should say, by the way, that one thing that you easily prove is that the value at 0 is 1. So indeed, you will get that zeros will be isolated and things like that. So, what is the function space that I was interested in here, and its dual? Perhaps more interesting. So, if you look at phi, which is of a function defined on the interval AB, then recall that the variation of phi, so that would be the supremo, sums of phi of xi, phi of xi plus 1, and supremo must be taken over all possible finite points, choices of points between A and B. And you say that if phi is of bounded variation, if and only if this number is finite. In that case, in particular, limits to the right, from the right and the left exists, and you might define the property, the quantity which is phi of A plus and phi of B minus. It turns out then that a norm, a suitable norm on the space of functions of bounded variations, is simply taking the variation and then plus absolute value of this boundary value here, the value from left, say right limit on the left-hand side and left limit on the right-hand side. And this is a norm on BV. What is then the small subspace that I'm looking for in BV? Because BV actually is too big. It's too big in order to do the direct analysis. And one reason being actually the dual is too small. So the smallest subspace that I'm looking for is a space which is, first of all, is defined as functions which are simply locally constant. Except for a finite number of points. So let me just give you one example. Oops. One example would be to say that you take a function which is, say, 1 here, then it becomes -1 there at alpha. It becomes 1 at beta, and then it becomes 2 to the right of beta. So that would be one example of a phi in my space. And why do I give you an example like this? It's simply because when you look at these kind of functions here, then you realize that you may describe them in terms of the jumps. So you have a certain number of jumps here. If you look at this function phi, I may describe it in terms of, say, elementary jumps. Let me define this for u hat in a plus b minus. I will define a jump function which is 1/2 if x is bigger than u hat, minus 1/2 x is smaller than u hat. Now, if you look at this function, then you realize that actually it's very close to the one I had somewhere else, over here, except that you have, in fact, inverted just the roles of the base point and the directed point. But the function phi that I have here, for instance, may be written as, say, from a given value here, you jump 2 values down. So it's like -2 sigma a minus. Then you jump 2 up here, so it will be 0 sigma minus. You jump 1 more here, plus. And then finally you add a constant value, which is 3/2, and I might write this as 3 sigma a plus. So this function is actually just the constant function 1/2 times 1. Now, any phi in my space may in fact be written as omega I, and then sigma ui hat for some finite combinations of this. And I should still add omega 0 times sigma a plus. Okay, so any simple function of this type can be written like this, and then you check that the norm of phi is simply the sum of the omega i's. So sum of omega I greater to 1. So this is like actually a small L1 space. And what we do is then simply to let x0 be the closure of S in bounded variation. So the small subspace that I was looking for in order to do this trick here, this is the closure of these type of functions in bounded variation. And why is that good? Well, it's because it has a nice dual. So x0 prime would be the Banach dual. And then given any L in x0 prime, I will define a function now on the space of point germs to be L acting on sigma u hat. So you take any sigma u of this hat of this type, you act with L on it, and then you get a number. I don't have the time to prove this, but then there's a very simple proposition, which is that if I take L in x0 prime, map it to L hat in the space B0. So there's one little thing, which is that on A plus and B minus, you happen to get just the same value, but with opposite sign. So I'm looking at H in bounded functions on A plus B minus, such that H of A plus, H of B minus is equal to 0. This map is an isometry, an isometric isomorphism. the B here being equipped with a uniform norm. Finally, so I should actually have stopped here, but 5 minutes.
We have to ask.
So I'll just give the principal lines of what's going on. Because we were looking at the dynamical system where you had IK, which say actually was from CK to CK plus 1. We had a map FK, which then maps IK to AB. I have a sign of monotonicity. And then we define a transfer operator. So the transfer operator defined in the beginning, which was given by Ruelle, was in the case interval here, I can write it in a slightly more complicated way, which is that I take phi, I compose with the inverse of the cased branch, except that I have to be in the image of the cased branch in order to do so. And now you look at how this actually acts on certain functions. In particular, if I act on a function which is in my space S, it suffices to look at what happens when I act on a simple base function, my sigma u hat there. So let me give you a drawing. So sigma u does the following. It looks like this. If I put, say, this point here, then this would actually be sigma u minus. And what is LK doing to this? Well, you simply look at the dynamics, and you see that you will map the interval to FCK, say, let's say f hat ck plus 1 minus. Now, the part which is outside will be chopped off because it's not in the image. So here you'd get 0. Then the point u here will be mapped somewhere here. And this would give rise to something like this if I have preserved orientation. And then here you will get the value 1/2. And then you will be mapped to this point here. And again, you will get chopped off outside. So what happens is that LK, acting on sigma u hat, would, after a long computation, you realize that when u is inside, when u is hat is inside the interval here, you get sigma, but at the image point. But you get two corrections terms because you have seen you're chopped off twice. So you get plus sigma bk of u hat, and then you get sigma fk hat b, oh, sorry, that's ck plus 1, cfk ck plus 1 minus, and there's another correction term coming from the other part, which is ck u hat sigma fk hat ck plus. So this took me, as I said, like 3 days to get the science right. But after I did that, then I came to the, say, nice conclusion. Which is that if you look at this expression here, then here you have a function that depends on u. I mean, there's a variable here, y, which I didn't write. But this function here does depend on u. Actually, this function here does not depend on u. It's just the same function all the time. This is the same function all the time. So this here will be the finite rank perturbation. And this here will be an iteration by the map f hat. So let me just say that sk h of u hat I define to be sk chi hat h of fk u hat. And pk, well, I'll perhaps omit the precise forms, but it's involving the correction terms there. Is defined, will be a rank 2 operator. And then finally the lk hat, which corresponds to how the lk acts in my dual space, is simply given by sk minus pk sk. Finally, if I sum over all the branches, I get an expression of the following form. So s minus ps, as I was indicating up there. And the s operator will simply be s hat of u hat, h of f hat of u hat. So a very simple form for the part which is using iteration of the f hat. And the p operator is a little bit more complicated, but it's say h of u. That would be sigma a u hat delta a of h plus, and then there's a sum sigma j of u hat delta c j of h. And finally, what are these delta c's, cj, h? That's h of cj plus minus h of cj minus. And there's one exception, which is delta a h, which is h of a plus h of b minus. So the upshot is that you get L is the sum of one operator here, which by evidence has spectral radius 1, because this is just plus or minus 1, and you're working on L infinity. So iterating here doesn't matter. So this has spectral radius 1, actually norm equals to 1. This here is, well, it's mapping to d plus 1 functions, so it has rank d plus 1. And then finally, you do the computation, and I won't do it, but you will actually drop into the expression which has now disappeared. Yeah, that has disappeared. But you will drop into the expression that if you calculate this determinant here, you will simply get the same as the Milnor-Thurston determinant that defined before. So when you finally reach this point here, what are then the conclusions you can draw? Well, first of all, it's nice to see that the intuition that you should have about the dual Ruelle operator being really related to Milnor-Thurston determinant is correct. Now, if the topological entropy is positive, then just from the fact that we know that the Ruelle operator is positive implies that the exponential of h top is an eigenvalue of the Ruelle operator, and it is the largest eigenvalue of the Ruelle operator. Which means that you get part 1 and part 2 of the Milnor-Thurston theorem for free without looking at any zeta functions. So, I mean, the Milnor-Thurston theorem actually drops out as a simple corollary of the fact that this is a dual determinant of the Ruelle operator, which is positive. And finally, the fact that it is a regularized determinant of the dual Ruelle operator was just very nice to see when I came about it. So thank you very much for your attention.
We have time for a few questions.
Vivian and I tried to make an extension of this Milnor-Thurston theory, allowing varying coefficients. And one other thing will be to try to find other extensions. What one uses as a basis is really the order structure of the reals.
Yeah.
is there some other structure that one might use instead? One thing that sometimes works is to use the conformal structure in more than one.
In the complex plane, yeah. Yeah, I remember you also had a paper with Sems, I think, you and Vivian, Stephen Sems.
We had people with SEMS and Dyer from somebody else. But they didn't.
You didn't go very far, perhaps. But the fact that, I mean, in some sense, the fact that working on the dual space, you also remember this paper of Levin, Sudin, and I forgot, yes, for the Ruelle determinant for hyperbolic Julia sets. And what they did is for certain types of weight, they could actually, instead of looking at the sum over pre-images, they could look at images of the critical point and then make a determinant out of this. So somehow there's this duality between the operator and then the dual operator, and the determinants you get from it is very intrinsic in some cases, and sometimes you might find it and sometimes you may not.
So maybe it's connected to David's question. I just want to point out that this, what you're doing here is you're really writing a regularized determinant, right?
Sure.
Because P is finite rank.
Yeah, so it's a regularized determinant of the dual Ruelle operator,
Right.
which is the Milnor-Thurston
Right.
determinant.
And actually you seem to want to avoid the zeta function, if I understood well what you said. But if you are interested in the zeta function, you can also study the zeta function by
You get it directly from this.
in any dimension. And this is what you did with Tsuji actually.
Mm.
So you can write the regularized, I mean you write the transfer operator as a bounded plus an operator which has a power which is trace class. And then you can mimic this reflection. But then you don't have this, you don't have any more the needing determinant, but you have a shortcut just to point out that this computation it can be.
It's used in other cases, yeah.
Yeah, the question may be on the same line. I mean, do you see or you don't see the periodic points appearing in the computation, or at least in the definition?
So in this approach, no.
But are there still? I mean, can you get information on them?
I would say the best information comes from Baladi Keller, which is that if you work on the real space of bounded variations, then they have this paper showing that you get a zeta function, which comes essentially from periodic points, and that has the same as eigenvalues as what I've been showing here. And if you do that, you can also show that I work on this smaller space, but I get the same eigenvalues, and the eigenfunctions that they would get in their space is in fact in my space. So there's consistency. I mean, I don't get more eigenvalues, and they don't get more eigenvalues than I would do in this way. But the periodic points, I don't see it all here.
Okay, so we thank both speakers again.